Okay, in this video, we're going to study eigenvalues, eigenvectors, and eigenspace associated with eigenvectors. You're going to see that. Okay, look, this is very, very important, okay? Study last two videos, because this third video will be based on these two videos that I'm telling you here, okay? Now, there's a definition of eigenvalue and eigenvector, okay? Eigenvalue and eigenvector, okay? That's a definition, okay? Okay, definition, there is no question, okay? That's definition, you have to assume that that is true. Okay, given a matrix A, okay, A will operate on X, okay, then you have lambda is a scalar, X is a vector, okay? This is a number, the real number, okay? A operates on X, and you have a multiple of this X here, okay, associated with lambda, okay? We can see here, let's assume, for instance, okay, that we are in the R3 space, okay? R3 space, okay? R3 space. Okay? Now, X1, X2, and X3. Okay? Let us visualize this right here. Okay. Here I have a direction, okay, that I call X. X. Okay? Look, I don't put arrow on X, okay? I know this is a vector, okay? Now, and I didn't put two arrow here on A, that I know this is a component of a second order tensor. Okay, now what this shows us that lambda x we can get here, lambda x, if its lambda is positive, greater than 1. But if its lambda is less than 1, I could have lambda x here. Okay, and if the lambda is negative, okay, I have lambda x over here. So you have to understand that in this direction there are infinitely number of solutions, but the direction is always the same. You see? Now that's a definition of eigenvalue and eigenvector, okay? The eigenvalue is this number, okay? Look, could be a complex number, but it's not, for the time being, we're not talking about complex, variable complex number, okay? Now, x is a vector. Now, very, very important, the components of the second order tensor, they are related to the canonical system. Here is E1, here is E2, and here is E3. You know that the size of E1 is equal to the size of E2, is equal to the size of E3, is equal to 1. Okay, this is a 3 by 3 matrix, okay? But what we learn here, we can generalize, okay, we can extend for n by n matrix, okay, matrix. Okay, now we understand what means an eigenvector, okay? This is a direction, okay, and lambda is a scalar. So A operates on X. What this operator does with X, okay? He move, okay? He change the size of this vector by lambda. Lambda is eigenvalue. Lambda is eigenvalue. Related to the vector x. Okay, this vector x we call here eigenvector. Okay, eigenvector. Okay, eigenvector. Eigenvector he associates with lambda. Now, you see here, okay, I write this right there. Okay, I can put, okay, the right hand side I can move to the left hand side. Then I have ax minus, look, if I put here just lambda x, okay, that's not good. Why? Lambda is a scalar quantity. This is a vector. Okay, I'll put here lambda ix. This is equal 0. Attention, here's a vector 0. Okay, this 0 here. Okay, in this coordinates, in this space, it has 3 components. Okay, don't forget this. This is a vector. It has 3 components. Okay, now here I can do like that. Lambda I x is equal 0. So x, this is a vector 0. Vector x is x1, x2, and x3. If I work, okay, with the R3 space, for Rn space I have any components, okay? I have any component for the 0. That's clear? Okay. Now, okay, which kind of equation is this one? Okay, this here is homogeneous system of linear equation. Okay, why is homogeneous? You see here, last 2 videos, we discussed this on the last video. Okay, last video. We discussed homogeneous system of linear equation. Okay, now we saw there that homogeneous system, there is only 2 ways to go. Okay, unique solution is the 0 solution, okay, or infinity solution, many solutions, okay, which is the case. Okay, I don't want a trivial solution. Okay, when you have a unique solution, see the last video. When you have a unique solution, then it's called trivial solution. We don't want trivial solution, you see, because we want, okay, many solutions in this direction. Okay, then I must a minus lambda I is equal to 0. Okay, this implies non-trivial solution. Okay, I don't want the trivial solution, because if x is 0, okay, this equation will be satisfied, but it will be unique. We don't want that. That's why this is very important. The determinant, not the determinant of A, is the determinant of lambda I, A minus lambda I, that is 0. Okay? Here, you have to pay attention to this. Okay? You have to pay attention. Okay? Because you give A, you think that we have to look at A, okay? But in this case, okay, the goal, okay, is A minus lambda I. That's very important, okay? Now, I put here what, why, and how, okay? For the time being, okay, I don't want to know about how I calculate, okay? I'm not interested in that. Okay, for the time being, okay? I'm sure in another video, then I will calculate, then I would say how, okay? Now, this is what and why, okay? What is eigenvectors and eigenvalue? I didn't say nothing yet about this, okay? What is this? This is by definition, okay? Then we're gonna see why we need this, okay? You're gonna see it, okay? Now, everything now I think is quite clear, okay? Now, let's make a point here, okay? Look, we are referring, okay, to the Cartesian coordinate, okay, the orthonormal system. Okay, now in the orthonormal system, do you remember this? Don't forget to see the first video now, okay? Now the second order tensor can be written A11 E1 plus A12 E1 E2, okay, plus A13 A1 E3, okay. Now A21 E2 E1 plus A22 E2 E2 plus A23 A2 A3 plus let's put here plus A31 A3 E1 plus A32 A3 A3 E2 plus A33 A3 A3. Okay, now the matrix A are the components of the second order tensor. Okay, now the components of the second order tensor looking at the bases E1, E2, and E3. You can see here. Also, the vector x, okay? I would say x1 E1 plus x2 E2 plus x3 E3, okay? That's our basis, okay? Now, canonical basis. E1, E2, E3. That is orthonormal basis. Okay? Now, we see this, okay, in the first video. Okay? Now, okay, I'll raise this. Okay? I'll raise this. And suppose I'm solving this homogeneous system. Okay? Look. A minus lambda I x is equal to 0. Okay? These are the components of the second order tensor, okay, in the canonical basis. Okay? This x is a vector in canonical base. 0 is a vector in canonical base. Okay? E1, E2, and E3. Okay? Orthonormal base. Now, let's do this. Okay? How can you calculate lambda? Look, I'll take this matrix here. Okay, determinant of A minus lambda I has to be 0, must be 0. Why? Because we want non-trivial solutions. Okay? I said about that. Let's write this here. Okay, look. Determinant of A11 minus lambda. Okay, here's A12, A13. Now, A through 1, here in the diagonal, I have A22 minus lambda. Here is A23. Now, A31, A32, in the diagonal, I have A33 minus lambda. Okay, this is determinant. Okay, there's a vertical line here. Why it affects only in the diagonal of matrix A? Because A minus lambda I. Okay, we know that lambda I is equal. Okay, look, I is 1, 1, 1 times lambda will be lambda, lambda, and lambda. I'm talking, you see, only 3 by 3 matrix. This could be generalized, okay, to for instance, 4 by 4 matrix, okay, 5 by 5 matrix, 2 by 2 matrix, okay? No, this is equal 0, okay? Look, when I multiply this, we see, okay, that here implies a polynomial of third degree, okay? Just this time, this, okay? When you develop, okay, the determinant here, this implies that I will have lambda cubed, for instance, plus or minus, we don't know, okay? Plus, for instance, alpha lambda square plus beta alpha plus c is equal 0. See? Now, I have to calculate this. Beta lambda, okay? That's a polynomial of third degree. We call this characteristic polynomial. Okay? I used to write this here as f of lambda is equal 0. Okay? This is characteristic polynomial. We can see here that's a third degree. If I have a 4 by 4 matrix, here's lambda to the power 4. If I have 2 by 2, it's lambda squared. Okay? Now, I have, in general, suppose I have the solution of this characteristic polynomial. Suppose I have 3 different values here. Real, okay? Suppose I have lambda 1, lambda 2, and lambda 3. Okay? How can I write, okay, I have lambda 1, lambda 2, and lambda 3. What I will do is these 3 values. Suppose, okay, I will erase here, okay? Look, I don't want this. I'll leave this here just for you to pay attention to this, okay? To understand completely, okay, this class, you have to study the previous 2 videos, okay? By the way, on the second video, I wrote as a title, okay, I put there, okay, I wrote system like that, okay? That's wrong, okay? This is why here, okay? A system, okay? Just for you to correct that, okay? On the second video, the previous video, okay? Now, you see what I will do. Look, a x1 is lambda 1 x1. Why? Because I have three numbers. Okay, I'm assuming that lambda 1 is different from lambda 2, is different from lambda 3. Okay, they are real, not complex. Could be complex. Okay, because the solution of the polynomial of third degree could be a complex number, but suppose are real. Now, I have here a x2 is equal lambda 2 x2, and the a x3 lambda 3 x3. Okay, I would like to call this, instead of x, doesn't matter, I would like to put a p, okay? You see why, okay? So a p1 is lambda 1 p1, a p2 is lambda 2 p2, a p3 is lambda 3 p3. Okay, look, pay attention. I'm not interested for the time being in how we get p1, p2, and p3. Okay, look at here. Okay, I'm just explaining what and why. Now I can look what is happening here. Look at that. P1, P2, and P3 are related, okay, to this canonical basis, okay? If I write P1, for instance, just for you to understand, P1 is equal, look, P11, P12, and P13, okay? If I have 3 by 3. If I have n by n, I would have here more components. The same form, P2 is 2, is 2, is 2. P3 is 3 here, 3 here, and 3 here. Okay? Just for you to pay attention to that. Okay? We are referring, okay, to the canonical basis. Now, I'll draw this possibility. Look how it's very, very interesting. Okay? Look how it's x1, x2, and x3. Now I have, suppose, my P1 here. Okay? Here I have my P2. Okay? And here I have my P3. Okay? Okay, let's draw here. Look. You see, look. P1, look. I don't put the arrow, okay? Okay? I know that P1 is referred to the canonical base, okay? P2 and P3 also. But P1, P2, and P3 are linearly independent, okay? Because I have one vector, another vector, okay? Suppose. Now, what is P1, P2, and P3, okay? They are, look at here, look how I'm going to write here, okay? A minus lambda I P1 is 1, okay? This is one equation, this is equal 0, okay? Now, here I will solve for P1, but I don't want to solve it for P1. What I'm doing here is just know that there is P1, okay? The other equation, A minus lambda 2I P2 is equal 0, and then A minus lambda 3I P3 is equal 0. So, if I want to calculate P1, P2, and P3, I have to solve this homogeneous equation, this homogeneous, and this homogeneous equation. Because I already know lambda 1, lambda 2, and lambda 3. But I don't want to calculate, okay? I know that they exist. I know that, okay? Then I drew here, okay? Now, I can consider, look at that, I can consider P1, P2, P3, okay, a basis in Rn space. In this case is R3 space. Then I have here two bases, okay? One is E1, E2, and E3. The other basis, okay, is P1. I don't put the arrow, okay? I don't put the arrow. E1, E2, E3, and P1, P2, and P3. Okay, Professor, how can I write E1, okay, in Cartesian coordinates? No problem. Look, E1 equal 1, 0, 0. Okay? What is E2? E2, okay, is 0, 1, 0. Okay? And E3, no problem. Look, 0, 0, and 1. Okay? Just for you to understand that this, look, this E1, P1, the components, I see the canonical basis. But P1, P2, and P3, by itself, okay, they form a basis, okay? That's a basis, Okay? That's a basis. E1, E2, and E3, okay, is a canonical basis. I have two bases, okay? One is E1, E2, and E3. The other basis, the vector, okay, that belong to this basis to span the R3, okay, E1, E2, E3 is span R3. P1, P2, and P3, which are the eigenvectors of A, look, the eigenvector of A, these also form another basis, okay? I have two bases. Now, I'm going to write here, understanding that, okay, I'll put like this, I'll write this here. Look how now things are becoming quite clear, okay? Look, I'll put all together, okay? I put like this, A, P1, P2, and P3, okay? Remembering that P1 has three components, P2 has three components, and P3 has three components, okay? Now, this is equal, now, look, A, P1, lambda 1, P1, A, P2, lambda 2, P2, A, P3, lambda 3, P3, okay? Let's erase here, okay, just to be more comfortable in writing this. Look at here. This is true, okay? Look. This is 3. Now, okay? You see that here I have three columns, and 3 columns, okay? Here I have 3 columns, no, 3, I'm sorry. Here I have 3 components, and 3 components. Obviously, I have 3 columns here. I have 3 columns there, okay? But when you see P1, you just know, okay, that P1 is P11, P12, and P13, because I am in R3. Like P2, P21, P22, and P23. Like this, P3, P31, P32, P33. Now, this is true, okay, because A operating on P1, okay, I have lambda 1 P1. Now, how can, okay, look, this I could say that is AP, okay? What is P? P is just this matrix here, okay? This matrix here, okay? Now, I can write A, for instance, in this case, 3 by 3. P is 3 by 1, okay? Why P is 3 by 1? Because here I have 3 components. Here I have 3 components, and here I have 3 components. I didn't write here, but I know that's there. Likewise, this one. Look, how can I write this? Look, this is, I'll do better, okay? I'll do better. I'll repeat this, just for you to understand better, okay? Look, A, P1, P2, and P3, okay? This is equal. Look at here. Look, P1, P2, and P3. That's a matrix. There's a space here. Now I'll write down here lambda 1, lambda 2, and lambda 3. Okay? This is 0, 0, 0, 0, and 0. Look at that. Look at that. Look. Now AP is equal P lambda. You see, I'll obtain here, in my lambda. Okay? Which lambda is there? Go here. On the first video, you're going to see that's diagonal matrix. Okay? Look, I obtained the diagonal matrix without solving those 3 equations. Okay? Because I just put P1, P2, and P3 without calculating calculate the components of each vector of this. Okay? Now, if you want, okay? I don't, okay, to get the diagonal matrix, The only, so AP is equal P lambda, okay? Now, look at here, A and lambda are similar matrices. Do you remember on this video here, I called the P as a magic P? Look, it's still, I don't know it. I don't know P. But I know P1, P2, P3 interfere on P. And this P, okay, is constructed by the three eigenvectors. Okay? Now, the magic P now, okay, I'm walking toward the magic P, okay, to open it, to know from where the P came, okay, and after how you calculate the P, solving the homogeneous equation. See, I didn't solve anything. I just got the diagonal matrix just knowing P1, P2, and P3. Okay? Now I can extend. Okay? I can extend that. Suppose I have 4. Okay? 4 eigenvectors. Okay? This is eigenvectors. Okay? Suppose I have 4. Then I have P1, P2, P3, P4. Okay? Suppose lambda 1, lambda 2, and lambda 3 are distinct. Okay? Then I'll have lambda 1, lambda 2, lambda 3, lambda 4, P3. And then my diagonal matrix will be lambda 1, lambda 2, lambda 3, lambda 4. I can generalize for any by n. Did you understand it clearly? Okay. Now, if you watch the first video, okay, paying attention, maximum attention, you see there how was Jordan's idea. Okay, what Jordan's idea? He said, okay, suppose there is no diagonal matrix. Okay, suppose there is no diagonal matrix for a certain matrix A. Okay? Suppose, okay, I couldn't find it. Okay? I'm trying to emphasize that I'm not calculating the eigenvectors. Okay? See, I have to understand that. Okay? I'm here, why and what. Okay? What I know, the eigenvector. Why? Because if I obtain lambda, see the first video, okay? This will help us to obtain the solution. See, the focus, okay? The goal is to solve AX is equals C. Don't forget that, okay? Now, if I have a similar matrix in diagonal form, okay, it's quite easy to calculate the solution of this equation because I decouple all these equations. I said this there, okay? Just go there and take a look and study, okay? Now, what Jordan said, okay? Now, suppose I have no distinct eigenvalue, okay? Now, suppose I have lambda, and lambda. Suppose I have 3 lambda right here. Okay, and suppose there is no lambda for a certain matrix. What Jordan thought, okay? Okay, I'll put 1 here, 0 here. Okay, I can put or not 0. Here 1. Or I put 0 here, or put 1 here. So I fill. This is my super diagonal. Okay, it's talking now. Super diagonal. Okay. When I put here, when I put 1 here in the super diagonal, this approximates, okay, for the diagonal matrix. Okay, because I cannot. Okay, given A, it's impossible to get a similar matrix in the diagonal form. But A is similar to J. Put it this way. Let's look. Okay. Now, let's assume, okay, that A, P1, P2, and P3. Okay, look, I put an asterisk here, okay. You see later when I will go through this how, okay. I put two asterisks here, okay. That's strange, but that's okay. This is equal. Now, I'll put the inverse here, okay. I'll put my here's P3 asterisk, and this is my Jordan, okay? Now I put lambda here, lambda and lambda. I'll put one here and one here. Look at that. Look, this is 0 and this is 0, okay? This is approximated, okay, to the diagonal form, okay? This is Jordan form, okay? Now, let's expand this. This is equal lambda, P1 lambda, lambda P1. Here, look at that. It's P1 times P2 lambda. Look, when I multiply this row by this column, what do I have here? P1 plus lambda P2 asterisk, okay? Now, let's see the third column here, okay? This row times this column will be 0 plus P2 asterisk plus lambda P3 asterisk, okay? You see, something new is happening here when I put the 1 and 1 there. Now, suppose Jordan, put here P1, P2 asterisk, and P3, okay? This is equal lambda P1, lambda P2 asterisk, okay? And lambda P3, okay? Let's put P2 here, okay? This is equal, okay? It will be different here, okay? Why? Because, look, in this case here, I'm doing like this. Look, I put 0 here, okay? In the super diagonal, I have 1 and 0, okay? This is valid for Jordan's idea, okay? Then you see later how you're going to put 1 here or 1 here, okay? You're going to see. I'm not interested in how for the time being. Now, I know here, okay, that this here, okay, let's put it here, okay? I can write P1, P2 asterisk, and P3. And here I will have what? In this case, okay? I have lambda, and 1 here, okay? This is 0, 0, 0, 0. Yeah. You see? Look, from here, I come to here, okay? If I put 1, 1, I'll come through here, okay? Look, if I move, I put 1 here and 0 here, I'm sure that will be this case. If I look, this is for here, okay? And this one we did before is 1, 1. Suppose I change here, I put 0 here and 1 here, okay? Suppose. Then what I will have, this is not asterisk, it's this one, okay? Now, it's not here, it's this one. Why? Look, when I multiply, this is here, okay? Look, when I multiply here, okay, P1 times 0 is 0, Okay? Now, P2 times 1 is P2 plus lambda P3 asterisk. This will be the last column. You see what I mean? So, playing with ones on the super diagonal, I can get different P's, okay? This P here is completely different from this P here. The Jordan here is completely different of the Jordan here, okay? And also this Jordan here. Did you understand that? It's clear. So, in the literature, okay, in videos, I'm doing just the opposite, okay? What in general you see in videos, you see in the books, you see the opposite. They start calculating diagonal matrix using lambda is equal P minus 1 AP. They do that. I don't care how to calculate gamma, knowing P1 and AP. You see what I mean? I'm doing just the opposite. First, I'm motivating what and why. Why do I need the Jordan? Why do I need? You know that because in the situation which I can't obtain the diagonal matrix, okay? That's why Jordan's idea was to fill, okay, the super diagonal with one, all ones, or some ones, some zeros, and so on. Did you understand? Okay. Our next step, next video, we're going to show how to calculate the eigenvectors, okay? I repeat, videos, many videos, okay? And books, first thing they do, they go through how, okay? I'm not interested in how. Before I motivate, okay, and then I calculate. You understand? Because what, why, and how is very important. To understand how, you have to know, you must know what I'm doing and why I'm doing. Okay? Then you see how. Okay? The logistic, okay, to act is what and why. Okay? How is a consequence. Okay? You motivate, then you calculate. Okay?